So the next operation we're going to be talking about is the differentiation operation. So the differentiation operation only requires a single signal and it will only be performed on channel 1. So this is why there's only one input and it's for channel 1 right here. So differentiation is going to be performed by operating the cutoff region of a high-pass filter. Now the problem with operating the cutoff region of the high-pass filter is that due to the roll-off rate, the attenuation can get very large for a large range of frequencies. So in order to prevent this, I have created 6 different differentiators that each differentiate for a different frequency range. So this one differentiates between 1 Hz to 10 Hz, 10 Hz to 100 Hz, 100 Hz to 1000 Hz, 1 kHz to 10 kHz, 10 kHz to 100 kHz, and 100 kHz to 1 megahertz. Now notice there's not a differentiator for any frequency higher than 1 megahertz. That's because if you recall from the probes, I'd set up anti-alias filters that filtered out anything higher than 1 megahertz. So we shouldn't be experiencing any signals with a frequency higher than 1 megahertz. So I don't need to account for those frequencies. So in order to perform this operation, there's a bunch of different inputs. See, there's 6 different differentiators, so that's 6 different inputs. If we try to run if we feed one signal into all 6 of these different differentiators, we might experience something called fan out. Fan out occurs when there's too many inputs in parallel to a signal. And if there's too many inputs in parallel, they might not be able to provide enough power to power all the inputs effectively. So in order to prevent this, I've created these extra buffers right here. So there's these 2 extra buffers. So this signal is actually fed into these 2 buffers. These 2 buffers act as a power boost and will divide the number of inputs. So that way this buffer with this input 1 will only have to supply power for 3 inputs, while this buffer with input 2 will only have to supply power to the other 3 differentiators. This way I'm splitting the amount of work done, so that way fan out is less likely to occur because we have multiple power boosters working on a smaller number of differentiators here. So like I said, this only operates on channel 1, so I just have to load in the channel 1 signal that we obtained earlier. So I load in channel 1 signal here, and from here, from this junction, it will be fed into these 2 buffers, and these 2 buffers will provide a power boost, and each only power 3 of these to prevent fan out. So we run the transient analysis for 1 millisecond. And so we run this, and run this all the way till it's done. And while we're waiting, we can look at plus or minus 12 volts again throughout the entire system. So when it comes back out, we notice we have a bunch of different waveforms on top of each other. Some of them look interesting, so let's separate these to look at them. So now you have to remember that our original signal was a 5 kilohertz triangle wave. So if we look at some of these other differentiators, their outputs can look kind of strange, but that's because they're not in the correct range. So this 100 to 1K kind of looks a bit wavy, but since our signal frequency is not in this range, I didn't expect this waveform to come out right anyway. Similarly, for the ones 10 to 100, it looks like it's looking like that. And then 1 to 10, it looks like it's railing at negative 10 volts. So the one that we really want to look at is 1K to 10K, because this is the frequency range of our signal. So notice how there's a negative, and then a negative constant, and a positive constant, and then 0. And now this makes sense because we think about what channel 1 was a rectified triangle wave, so that it only had the positive peak. So that peak had a negative slope, and then a positive slope, and then no slope because it was 0 or constant, and then it repeated itself. So this is the type of signal that we should expect from a differentiator. So from here, we just have to export this out as a text file as per usual. So I'm going to call this differentiation. I'm going to save this. Now I have to open it up in Excel again. So if I open up in Excel, open it up here, differentiation, open that up, tab delimited. All right, looks good. So if you look at the number of samples, you notice the number of samples has increased to approximately 10 times. It's actually 4,500 here, but it's approximately 10 times. So I can filter out, I'll need to filter out every 10th sample when I split it. So then I just need to run the filter macro, which will filter out every 10th one and separate them. I will overwrite the previous data that I ran here with this new data. All right, so now I just need to save all these as text files so that way they can be imported back into there. Overwrite this data. Need to overwrite this data. All right, next we need to overwrite this data with the text tab button. All right. This one. Okay. 10K to 100K, so that is saying 100K to 1 mega. All right, this should be the last one then. Okay, so after looking through all these, the system, as you noticed, took the channel input and just performed all 6 of these in parallel. It didn't even check which one was the correct range. So it technically has all these outputs, but now it needs to choose the correct frequency range in order to display the correct output. So in order to do that, we have the separate circuit right here. Now this is just another one. This is just a simple analog mux, and it's going to pick between the different frequency range outputs that we had obtained earlier. So first I should just quickly load all these back in. So this is going to be differentiator 110, okay? This is going to be differentiator 10 to 100, okay? This is going to be differentiator 100 to 1000, okay? This is going to be differentiator 1K to 10K. This is going to be differentiator 10K to 100K. Okay. This is going to be differentiator 100K to 1 mega. All right, so now we just have to choose the select lines based on these switches. So if I want 1K to 10K, I need this S4, but S4 is actually, if we look here, we start at 000, 001, 010, and 011. So I need 011 here. So in order to get 011 here, I need to set the MSB, which is this bottom one, to 0, this one to 1, this one to 1. So that way it's 011, so I select this channel at the output. So then I just run the transient for 1 millisecond. And then I wait a bit and so I let this run. But when it comes out, you see this is the waveform that we selected earlier. It has negative constant, positive constant 0, and it has the highest, and it has an amplitude of 600 millivolts. Now, I told you earlier that it runs in the cutoff region, so there's always going to be attenuation. So unfortunately, these values may not be scaled properly, but the general shape will be the correct differentiation shape, but the scaling may be a bit off. So with that, we have to export this out because this is what the differentiator will output to be. So this will be the differentiation operation right here. And this will be routed all the way to the output selection at the very end. But before that, I want to make sure, and it's always important to do this every time you export. Every time you export, you need to check the number of inputs to make sure that they're reduced to 10 times less, because since we used an output, there should be 10 times as many samples as before. So we'll need to reduce the number of samples by a factor of 10. That is performed by using the macro, the filter samples macro. So I'll quickly run the filters samples macro. So now we have 1/10 of the previous number of samples. So it's a much smaller number. That way the processing time will go way down. So then I just need to save this as the text file with tab delimited. All right, so this is differentiation select because this is the one that we selected. So now this output is good to go. So with that output good to go, this differentiation output will be routed to the operation select at the very end after we've covered all the operations. And then from there, we'll be able to select which operations we want to output to the digital display.